side.
Yeah, thank you very much for the invitation, and I do apologize that I cannot participate personally in Wildau. I will try to share with you the last subject that engaged me in research now. Let me say if the slides are changing. Is it changing?
It's changing, yes.
The second slide now?
We see now a slide with synopsis.
Yeah, exactly. Yeah? Okay, so the plan of the presentation is here. So I will introduce shortly, I will explain what is virtual teleportation, which is very interesting technology that we use, and also the combination of autonomy and virtual teleportation. And some very important problem, how to switch in between, which depends on detection of two difficult situations for the control system of the autonomous robot, and some examples of application, and finally I will conclude. So, first of all, I will make some difference, or you know it, but maybe it's important to remember. What is the difference between the automatic vehicle, for example, and autonomous vehicle? So the automatic releases the operator from some activities, as for example, ABS system in the car. But autonomous vehicle is a fully automated vehicle, which completely removes the driver from the vehicle and needs any human intervention. So here's a very good example of the autonomous system, very boring activity, and it would be nice to have this system working autonomously. However, there are several situations, as presented here, when the autonomous system cannot operate autonomously. It's very difficult and maybe impossible to build a completely autonomous system, because in any time the system may be faced with a situation which is impossible to solve by the system itself. So, for example, here the system is unable to drive out from this trap, and the answer is to call the operator to help the system to escape from the situation. So the autonomous system that I use in this presentation, this is very historic model of the system, receives some signals, very, very generally understood, process the signals, and also in the homeostat, which is the organ that can modify the structure of the system, make some reasoning here, and also converts the energy, which may be also on board, and applies the energy to the effectors, by means of which the system can affect the environment. Very nice model is presented here, an intelligent mobile robot, maybe very, very funny figure, but it very good points out the idea. So we have the environment, and the environment is sensed by percepts. Percepts are collected by sensors. And this question mark represents the brain of the agent. Brain, maybe we should understand very, very broadly. And processing the percepts, the agent finds the actions, and the actions are carried out by means of the effectors, and the agent affects the environment. And finally, the third concept, which is necessary to understand my lecture, is the fault-tolerant system. And one of the models is here. So the system may be affected by some faults. Fault may be understood very generally. And here we have some subsystem for fault detection and isolation. And finally, fault-tolerant control, which allows the reconfiguration of the system in order to be able to operate in the situation when the fault affects operation of the system. Teleportation. Well, maybe some very funny citation. What is meant under the teleportation by Harry Potter. So depart from one place and apart in another in the same time. And very funny situation here. You can learn it at school in the 6th year, and it requires concentration, and maybe it's dangerous. What is virtual teleportation? Some locomotion technique that allows users to navigate between the confines of available tracking space with the low possibility of inducing some sickness. And finally, holoportation. Holoportation consists in embedding the person into the environment using some holography. So the 3D capture technology locates the person into the environment. We develop virtual teleportation, and we understand under the virtual teleportation some special functionality of the user interface that allows the full immersion of the user in the environment that may be distant. Distant means maybe in the second room, but also maybe on Mars, for example, and thus to create the impression in this operator, which is received by the senses of the user, as if the person were in this distant environment and could personally act on this environment, maybe only observe the environment, but maybe also change the environment. And our approach depends in the application in the real-time scale, which is something other than, for example, web pages which allow you to visit some historic ruins or so. You can move along the walls, etc., for example, but it's not in a real-time scale. Somebody videotaped this environment and made it available on the web page and allowed you to visit this virtually. So the history of our development of the virtual teleportation started in 2012. And the early conception was prepared by my friend, Professor Krzysztof Cyran from the Silesian University of Technology. Then we applied for many projects. And you know, I'm the machine for writing applications and for not obtaining, unfortunately, the applications too. Several of applications we obtained, but several were unsuccessful. I will be speaking about them a little bit more later. So how we get the virtual teleportation? We need to make acquisition of perceptions on the remote stage, which is distant from the stage at which the operator is residing. Then we need to transmit the images and signals to the operator. And we need to make, to achieve the virtual immersion of the operator in the remote stage. This is a passive virtual teleportation, but also we develop the active virtual teleportation, which requires acquisition of the operator's reaction of the current situation. I will be speaking about this a little bit more later. Then transmit the control signals to the actuators on the remote stage. And finally, the actuators should act on the objects or processes which are located in the remote stage. And this is the active virtual teleportation. How we can acquire perceptions on the remote stage? Now, first of all, we can collect images and scenes by means of stereo images. We need cameras for this, or omni cameras. We can record and transmit sounds. Stereo sounds are more valuable in this case. We can also, for example, collect fragrances, which may be represented by means of vectors of components of the fragrances and reproduced then at the remote scene. We can measure touch or mechanical resistance, etc., by means of measuring forces, pressures, and many others. And for this, we can use, for example, artificial leather or strain gauges, etc. For data transmitting, and which includes signals and images, we usually use wireless transmission. And in case of wireless transmission, there is the problem with the range, which was, for example, presented by the presenter that preceded me. There are also transmission costs, which maybe should be included, and also delays. Delays are very essential here. How we induce the feeling of immersion of the operator by means of realistic reproduction of signals and images. So we need some special interfaces, the acceptable delays, and also we teleport the human to the remote scene using either virtual or augmented reality techniques. How we acquire the operator's reactions? First of all, we use some devices for control, different controls. I will give you examples later. You also can use voice commands or natural language messages. We can use gestures, very, very interesting. And we had also here some results in this area. We can use eye tracking, for example, and also tracking body movements. But also, and this is very interesting for us now, we use the facial expressions just to establish the symptoms of the mental state of the operator. How we combine autonomy with virtual teleportation? So generally speaking, autonomy may be applied to any class of the automation and robotic systems. Examples are here, for example, autonomous laboratory system. We apply now for laboratory, automated laboratory without humans, which belongs to this class. It can be agriculture tractor, for example, or autonomous UAV, or maybe Mars rover also. And generally, autonomy relates to control. So it may be extended to decision-making also. And in case of mobile system, we also assume that the system, for example, has some autonomous power supply on board. Depending on the class of tasks the system is devoted to, we can, from left to right, make ever more and more complex problems to solve. When we have the system which follows a predetermined program, so it's the easiest system. For example, the agricultural tractor, whose program is defined before starting the operation on the field. And we distinguish here between static and dynamic environment. Static environment does not change during the operation of the system, and dynamic can change. For example, on the field, there can arrive, for example, lorry, which was not at the beginning of the work, and the system has to operate and to avoid collision with the lorry. Reacting systems is the more advanced class of autonomous systems, and they react at the situation in the environment. And finally, exploring systems maybe are the most sophisticated because they plan its operation according to the development of the situation in the area they operate. Where is the place for the virtual teleportation? Several examples are here. For example, supervision of the autonomously operating system control in the macro scale. An example is here connected with the Mars rover, because you know that the transmission of signals from Mars to Earth takes several minutes. So we only can control the rover in the macro scale. And in case of facing any difficulties, it may stop, should stop and control and connect the operator on the Earth. Remote experimentation, very interesting thing, was developed in Poland by one of the institutes. So the students could carry out the experiments at the laboratory stands, which were located in the city Radom in Poland. And those experiments were carried out according to the commands that were issued by people that were distant from this laboratory. And maybe the most important, and I'm focused on this application, is the temporary replacement of the autonomous control. There is some similarity between the semi-autonomous system and fault-tolerant systems. For the fault-tolerant systems, the general algorithm of operation is as follows. The system operates and checks if it operates okay. If yes, it repeats this loop. If not, the reconfiguration of the system is carried out. In case of autonomous system supplied with the virtual teleportation, the system operates and answers the question, can I act independently in the next step? If yes, it remains in this loop. If not, I'm contacting the remote operator. And the operator takes over the control and solves the problem the system is unable to solve by itself. So the most important problem is to detect the situation which is too difficult for the autonomous system to solve by its own. So the general remarks are as follows, that this is some special kind of fault. So in this situation, we can solve the problem using the methodology for fault-tolerant systems. So we need to detect the situation which is too difficult for the autonomous system. This detection may be supported by a knowledge base, and we have two variants. The first one is reactive. The mobile robot cannot drive through the sand, for example. And in this situation, which currently exceeds the ability of the autonomous control, so the system needs some help from the remote operator, but maybe also prognostic. For example, the tractor works on the field, but knows that after 100 meters, there is the ground which is too wet, and it will be unable to travel using autonomous control. What solution we develop here? We develop an expert system, which may be, for example, rule-based, and we apply here induction or analogy for reasoning. We have several types of rules. The simplest is rules of operation in reactive variant to the internal state of the robot. So the internal state is not good, for example, too hot within the corpse of the robot. So the method of operation maybe is defined in the knowledge base, or the robot cannot operate in such a situation, so we need some help of the remote operator. Another combination is a combination of the internal state of the robot and also state of the robot's environment. Two kinds of rules here. And the last one includes, so there's a prognostic variant, which includes also plans that the robot knows and knows that the next task to be solved is too difficult for the control system to be solved by its own. Here we are faced with the non-monotonous reasoning because you plan to present my presentation in the internet. Maybe for somebody will be interesting what is meant under the non-monotonous reasoning. It means that the scene changes and facts collected change during the operation of the robot. Here is some example of the very general algorithm. So we seek for the rule whose premises are matched by the collected percepts and also features of the internal state of the robot. If we find any, we make the action that is defined in the rule. If not, we simply call the operator. This system can learn. This is the better solution for the system that combine the autonomy with virtual teleportation, because the system can learn from the virtual operator, from the remote operator. So it contacts the operator, but it observes the operator during the solving of the problem and adds additional chunk of knowledge into the knowledge base to make it possible to operate autonomously in the same situation in the future. And now we come to the examples. So the first, our approach was the adventure. Adventure was virtual teleportation technology for controlling cargo aircrafts during the flights. Everybody of you who flies with the planes knows that the pilot is necessary mainly to give the passengers some safety feeling that the pilot is on board. Because maybe 99% of the flights are controlled by the autopilot. And we wrote an application for the FP7 European program, in which we assumed that the pilot can remain at the airport. And in case of too difficult situation for the autopilot, the pilot remaining in the airfield can control remotely the plane to solve the problem. Unfortunately, this is the decision that we got there too futuristic. You know, yesterday one of the presenters showed taxis which fly now autonomously. So it is on the 9 years. It was too futuristic. The second approach was Telerescuer, our flagship project, system for virtual teleportation of rescuer for inspecting coal mine areas affected by catastrophic events. This is the informal opinion of reviewers, enough crazy to be financed, and we got this project. I will show you some ideas concerning connected with this project. Here is the part of the coal mine, and in this area, some catastrophic event occurred. So in the coal mine, the people built some dam which closes this area. And this area is inaccessible for the people because there is an atmosphere which is explosive atmosphere, and also it is too hot maybe, and many factors that make impossible visiting of this by humans. And you created a robot which was equipped with sensors, collected images, measurements, signals, which were transmitted via, as you see here, cable to the station, which was located in the safe place of the coal mine. So the scene of the operation of the mobile agent is inaccessible or dangerous to humans due to high temperature of poison gases, for example. There are obstacles difficult to traverse and also limited range of wireless communication underground. And this area is closed by the dam. Look what is the situation after the explosion or fire in the coal mine. It's a dramatic situation, and we had to design the robot which is able to move along such, for example, area. So the system was equipped with a special vision system based on stereo cameras and also fisheye camera and infrared cameras with lighters. And also operator station took advantage of stereo vision. And in some sense, it created the impression for the operator as if he or she were in this area where the robot is now operating. Controls that were used by the operator. So using those controls, we can acquire reactions of the operator to the situation in the remote scene. Another project that we carried out in our subsidiary company, supervising autonomous mission of unmanned blimp by virtual teleportation. The object that we created was the blimp filled in with the helium. And our problem that we can report now depended on this, that it was, so the particles of helium are very small. And it's necessary to have the envelope which does not allow those particles to go out from the envelope. This was our main problem in this project. We developed some virtual teleportation interface to this project. This is based on the Oculus, but we also used the HoloLens of Microsoft, in which we implemented the gesture control. So we could control the blimps by means of the gestures. Another example of the project that we didn't get, unfortunately, is the electric bus in the depot. So the electric bus in the depot, after arriving at the depot, several service operations must be done. For example, diagnostics, maybe small repairs.
Dear Professor, I'm so sorry, but we have 2 more speakers. Please.
Yeah, I will go to the end. So in very difficult situations, some remote driver can help the bus to park on the park place. And the last project that we have now consists in developing the drone, stratospheric drone for profiling emissions in the atmosphere. And here we also apply the remote control in case of landing and takeoff. Going to the conclusions, the idea is developed by the company in the collaboration with the university. And regarding the implementation, it requires interdisciplinary research. And the autonomous systems require building the knowledge base which supports decision when it is necessary to call the remote operator. Several projects that were used here for developing this technology and the contact information for me. Thank you very much for your attention.